Hello everyone, this is Icon, and today I'm going to introduce the epsilon delta definition, which is the first kind of mathematical thing in your calculus, in your university calculus. And the first question will be, why do we need the epsilon delta definition? That is really a good question because in high school we already have the notation limit x approaches c, f of x equals capital L, which means if x and c are close enough, and f and L will be close enough as well. But this is quite ambiguous because we don't know what approach means, right? And we don't know how can they approach as well, and how close can the approach be. Also, can we compare or relate two approaches? Those things we don't know so far. And I have to say one more thing is that was the notation. The notation means that we use the words to show what we want to say. So that is actually just literally notations, which can be turned into other ways, such as f of x tends to L when x tends to c. This is equivalent with limit x to c, f of x equals capital L. We have another notation as well. F of x approaches L when x approaches c. So these three things are the same. And actually here, the equal sign does not mean the real equal. It implies a kind of approach in that equal sign. Okay. And the real definition goes here. For all epsilon, which is greater than 0, then there exists delta, which is greater than 0 as well. Then, for all x in this inequality, which I will explain later, for all x in this inequality satisfies f of x minus capital L, which is less than epsilon. This is the definition of limit x to c f of x equals capital L. This notation, which is equivalent to the two that I just said, f of x tends to 0 when x tends to c. Okay, so this is called epsilon delta definition. Epsilon delta definition. And I have to say that in this definition, there's no such word approach, right? We just need to take epsilon, like any real numbers is fine, any real numbers, and delta, any real numbers as well. So we don't have the concept of approach in this definition. We use the alphabet instead. And I have to explain the alphabet here, the epsilon. And here, epsilon means the distance or the limit of distance between f and L. Okay, you can see here. The absolute value means if you have A minus B, if you have A minus B and you put absolute value on it, then this means the distance, right? This means the distance between A and B. So here we have the distance between f of x, and L, f of x and L. And you have to note that this is the variable. This is a variable. This is a constant. This is a function, and this is a constant. You have to say that epsilon is greater than f minus L. And you can decompose the absolute value. So we have minus epsilon, which is less than f of x minus L, and less than epsilon, right? So these two are equivalent. And also, we can add plus L in 3 places. We have this inequality. Okay, so here is the y-axis approach. Here's the y-axis approach. And we talk about the approach on the x-axis. And in x-axis, we have 0, which is less than x minus c, less than delta, right? So equivalent to, let's see here. Let's ignore the 0 part, okay? So we have minus delta, less than x minus c. Then we add plus c in 3 parts, okay? So c minus delta, less than x, less than c plus delta. These 3 are equivalent. And going back to this 0 part, we can't let x minus c equal to 0, right? So we have to take 0 out from this inequality. So we can take the range of x, let's say D, the set D. So x will be in C minus delta in the open set, C minus delta, and union C plus delta. And we can draw a graph about these things, which will be like here we have L, and here C. The red one will be epsilon. So we will take epsilon here, and here will be delta. Okay, so let's take one example here. Before that, I have to say this one. Like for all epsilon, which is greater than 0, this is kind of tricky because actually any real numbers are fine. So some students may say, may I take a number that is greater than 0 but less than other real numbers? So suppose we have a number alpha. So the question is, may I take this alpha equals to epsilon or delta? This is a question. And actually, alpha doesn't exist. Because if you take any other number, just like alpha over 2, alpha over 2 is less than alpha. It doesn't satisfy this inequality. Right? If you take beta equal to alpha over 2, so this inequality is not satisfied. So there doesn't exist an alpha such that which is less than other positive real numbers, and also greater than 0. So there doesn't exist an alpha satisfy the property. So we just need to take any real numbers, like any is fine. So we can have one example here. We have to show that limit x to 2, 5x is 10. We have to show this limit. So we can apply the definition directly. Like these two parts are equivalent. So if we can have this part, and this part will be shown. Okay? So we may say let epsilon, which is greater than 0, let epsilon exist. Then there is a delta. There is a delta. How can we find delta? I will say the answer first. The answer here will be epsilon over 5. This will be shown later as well. Then we take delta equal to epsilon over 5. Then we have the inequality that for x in 0, which is less than x minus c. The c here will be 2, right? And less than delta. The delta here will be epsilon over 5. And satisfies f of x. F of x here will be 5x minus 10. The 10 here is the L. And less than epsilon. Okay. And how do we show this sentence work? We just need to see this inequality. So x minus 2, the absolute value of x minus 2 is less than epsilon over 5. Then we multiply both sides by 5. So we have 5 times of x minus 2, which is less than epsilon. Then we take the 5 into its absolute value. Then this inequality appears. So this is quite trivial. Okay. Therefore, limit x to f of x x is 10. Okay, and we take another example here. We have limit x to c, something is k equals k for all k belongs to real numbers. Okay, and this is quite trivial as well because we can choose any delta in the real numbers k minus k, which is f of x minus L, is always less than epsilon. Because epsilon is a number that is greater than 0, and this part is 0. Let's look at another more difficult one. We have limit x to 5, x squared is 25. And we have to show that for all epsilon, which is greater than 0, there exists a delta such that for x in this inequality then satisfies this equality as well. So we have to find a delta such that x minus c is less than delta, okay? And here we can use some tricks. We want to find a delta, but we want to find the epsilon before we find delta. So we want x squared minus 25, which is less than epsilon. So we can factorize the inequality. And here we have the x minus c part, right? Here we have the x minus c part. So can we just put this into the right side and let this x plus 5 absolute value become the denominator? Actually, no, because you don't know what x will be. Okay, so this part will be a real number instead of variable. So we have to kind of limit where x can be. So suppose we have to suppose a number that limits the range of x, and you can put any number here, and I just want to put 1 because 1 is simpler. Then you can add 10 in these three parts. So you have 9 less than x plus 5 less than 11. So we can have the inequality that x plus 5 is less than 11 because we have here will be the range of x plus 5 and here is 0. So the absolute value of x plus 5 is definitely less than 11. Okay? This is acceptable, okay? So in the case of x minus 5 is less than 1, we have the conclusion that x plus 5, the absolute value of x plus 5 is less than 11. So we can go back to this, go back to here, then we have x minus 5 times 11. Here it's less than x minus 5 times 11. Okay, then we want it to be less than epsilon. So we can take, we can have the formula, or we can have the inequality that x minus 5 actually is less than epsilon over 11, and we can take it. So here is what we want, and actually we can find the delta from behind. So take delta equal to 11 over epsilon, the minimum of 1 and 11 over epsilon. Because here you have limit the range of x, right? You limited it into like x minus 5. The absolute value of x minus 5 is 1, less than 1. So you have to take minimum of 1 and epsilon over 11. So if you take epsilon equal to minimum of 1 and epsilon over 11, then for all x in this inequality less than delta equals to 11 over, epsilon over 11, then this inequality will be satisfied as well. Therefore, limit x to 5, x squared will be 25. Going back to the first example, we have limit x to 2, 5x is 10, right? And I said that choose delta equal to epsilon over 5, right? And we had limit x to c, k is k, right? But actually, I didn't say how to take the delta. But how to take delta? Actually, this is quite simple because you can see the rules from some examples. And I'll tell the result first. So if you have a linear function, alpha x plus b is alpha c, alpha times c plus b times c plus b. You want to show this, then the delta will be the absolute value. Denominator will be the absolute value of alpha. Okay. You can take the alpha out, then x minus c less than epsilon. So these two are equivalent. Then we want this part to be less than delta. So we can divide the absolute value of alpha for both sides, x minus c, which is less than epsilon over the absolute value of alpha. Then we can take this to delta. So here we have the conclusion that if you have a linear function, then the delta will be the coefficient. The delta will be epsilon over the absolute value of the coefficient of the x. And one more question is that why does it goes for all epsilon exist delta instead of for all delta, or exist delta then exist epsilon, or for all epsilon? This is quite intuitive, because if you have a function, I don't know what would be, but just like this, and you want the result. That the limit of the function will be L. That is the result. So you want the result, but you limit the range of delta